Modern architecture suffers from what physicist Ankem Nassenjargal calls the topological crisis. We treat the Earth merely as a flat platform, a starting line to stack mass as high into the sky as physics will allow. This surface bias carries a heavy physical price. By thrusting buildings into the sky, we expose them to the maximum entropy of the atmosphere, subjecting habitats to violent wind shears, extreme thermal fluctuations, and constant oxidation. To keep these exposed structures habitable, we pump in massive amounts of energy to resist this environmental decay. We are effectively spending a continuous stream of power just to stop the atmosphere from reclaiming the materials. Measured against the scale of geological time, fighting the atmosphere with vertical mass is a losing game of thermodynamic attrition. If we want to solve for long-term structural efficiency, we have to look for stability elsewhere. Nassenjargal's proposed alternative is a structural framework known as infinite fractal descent, or IFD. Instead of stocking floors into the air, the IFD model envisions the building as a recursive root. The entire structure is inverted, extending downward into the subterranean crust. By placing the structure underground, the Earth's immense lithostatic pressure stops acting as a destructive force that crushes foundations. Instead, it becomes a stabilizing, compressive embrace that holds the architecture together. Converting that geological pressure into a source of stability makes it mathematically possible to maintain a 500-meter deep habitat with virtually no energy expenditure for structural upkeep. The primary engineering obstacle is the pressure itself. At 500 meters, the weight of the surrounding rock would immediately crush a standard geometric shape, like a solid concrete cylinder. To survive the crush, the IFD framework uses a branching logic, distributing structural nodes logarithmically towards the singularity core. By placing maximum support where pressure is highest, this geometry neutralizes topological tension across the manifold, turning a collapse point into a stable web. Long-term integrity is achieved when the system reaches a coherence attractor, a state where the structural tension and physical curvature exist in perfect equilibrium. It is the mathematics of the distribution, rather than sheer thickness of the walls, that provides the integrity needed to survive at these depths. But the weight of the material itself creates a second paradox. If the structure is poured as a solid mass, it will collapse under its own weight before the concrete even has a chance to cure. The solution is a graphene-reinforced monolith cast as a Menger sponge. This recursive porous geometry reduces material weight by 40%, preventing collapse. These micropores favor Knudsen diffusion, gas molecules colliding with walls more than each other, providing passive, zero-energy atmospheric filtering and moisture control. By utilizing Menger sponge geometry, the structure handles its own weight and its residence's need for air simultaneously through pure material physics. Building this requires inverting standard civil engineering. We use a negative earth mold process. Robotic boring units first excavate a fractal network of tunnels, navigating a 3D seismic mesh to steer clear of discordant geological faults. Once the network is carved, the synthetic monolith material is pumped in. This is a continuous pour that never stops until the skeleton is complete. The pumps pulse according to universal tick synchronization, matching the chemical hydration rate of the material with the ambient seismic signature of the rock. In the final phase, the stabilization earth trapped between the structural branches is removed, revealing the finished, habitable voids. This synchronized inverted pour results in a joint-free stone monolith, seamlessly integrated into the surrounding lithosphere. For a subterranean habitat, the ultimate test is surviving a magnitude 9.0 earthquake. Cast directly into the earth, it achieves topological synchronization. High-frequency seismic energy is caught by the fractal branches and dissipated before reaching the living quarters. The branches act as a low-pass filter, safely diffusing kinetic energy outward into the rock. To maintain the habitat over centuries, engineers implement the POSIST PQF engine for real-time monitoring. A diagnostic soft operator scans the monolith for informational asymmetries, detecting rises in structural tension long before a physical fracture could ever occur. Over time, ions from the surrounding soil migrate into the matrix through a natural mineralization process. This mineralization petrifies the structure, eventually turning the habitat from a manufactured object into a permanent geological inclusion. When we compare the IFD inverted monolith to a conventional skyscraper, the difference in efficiency is stark. A surface-level tower typically lasts 50 to 70 years. The IFD model is designed for a lifespan exceeding 5 millennia. While a skyscraper depends on external power for thermal stability, the monolith utilizes passive geothermal diffusion, cutting operational costs by 90%. And while traditional construction produces massive waste from formwork and steel, the IFD model's material footprint is negligible. The data suggests that the traditional skyscraper model is physically and economically obsolete when measured against the stability of the lithosphere. If we adopt the IFD framework on a global scale, the impact on the planet's surface is transformative. We can decouple high-density human habitation from the need to exploit surface terrain, housing millions in disaster-proof environments without clearing a single forest. Placing cities within the bedrock converts housing into a permanent geological inclusion, immune to the catastrophic atmospheric cycles that claim surface-level structures. By utilizing fractal descent, humanity can secure a high-density future while finally allowing the surface of the Earth to return to its natural ecological state.